Welcome everyone to the ARM instruction set architecture part 2, continuing here with ARM v8 aka Aarch64 or simply A64, the super amazing ARM numbering here, of course, meaning, as you probably guessed from ARM v8 64-bit instruction set, that certainly makes total sense, as much sense as it makes to call it Aarch64. This ARM, as you see from the part 1, developed since the 1980s, 85, 86, the first working implementations, and ARM v8 64-bit since already 2011. Here announced October 2011, ARM v8, often called ARM v8. You see totally amazing numbering that makes sense. Not what ARM also has done, what I've not seen so in all the early, like all the first decade of 1998ish to 2011, I only ever heard ARM, like ARM 1, 2, 3, 4, 5, ARM version. Like I said previous video, all the confusion here of, we probably have this here also somewhere, ARM version, let's see, 6. Just what I said in the previous video, this mismatch of, in my opinion, totally avoidable mismatch of architecture versus core here of numbering, super confusing. This was already confusing enough for me the first decade, but the first time I've seen Aarch, then with the 64-bit architecture, they made it even more confusing and called this new stuff Aarch64. Back in the day, it made totally zero sense to me why to call this Aarch64. Whatever, somehow marketing names is not the best that I'm holding, and because I certainly would have called this ARM64, but what do I know? Certainly, so for the first years, I always heard Aarch64. I personally always refused to call it like this. All my customers always like, what are you freaking talking about? So I personally always called it ARM64 because, YOLO, whatever. Somehow, I think later, some years later, ARM probably realized, whatever, nobody really likes this Aarch64 name. Funny enough, they called the old stuff then Aarch32 because seriously, what the heck? You could call it ARM32, but that would certainly be too simple. And then some years later, I saw them using A64 and A32, as you see here. Now named A32 is like, even that name is like, why not name it ARM32 and ARM64? But somehow big companies, big management, playing golf and making up numbers. It's probably what you get for your CEO golfing. But anyway, Aarch64 and 32 and stuff and A64. So what did this give us? This new stuff? Don't tell me I clicked there wrong. Darn, I really clicked there wrong. How can I? Where is my... This probably so much to closing here, what we had already open. On Safari you could control set this, but apparently not in Firefox. So ARM version 8, because it's, as I said, Aarch64. I'm not making this naming, it's the naming ARM goddess. So what they changed? They changed quite a lot, you would think, similar to Spark, MIPS, even x86 of AMD 64 and RISC 5, you would think, hey, the stuff is, why do I make a dedicated video about this? It's still the same, right? No, wrong. If you guessed it, you just take ARM32, let's call it something same, right? ARM32, and you make everything 64-bit wide and you're done. No, not so much at ARM Holding. They innovated a little bit more. And they probably realized that what I said in the previous video in part 1, I said the topmost 4-bit conditional codes for conditional execution might not have been the best bits spent in the encoding space there. And the engineers and researchers at ARM apparently arrived at a similar conclusion, and they entirely removed this from A64. So this is why Aarch64, A64 ARM is entirely different. I've never seen something like that in any instruction set. If you have another example, leave this in comments below. But that also makes writing an assembler and compiler a little bit more difficult, because normally you would think, hey, you have a 32-bit compiler, you just change this a little bit to 64-bit data types and you are already halfway done. In ARM, it's a larger re-engineering, even for the assembler and stuff. So they most likely have done this because they probably, with simulation and research, came to the conclusion that 16 general purpose registers don't cut it in 2011. And they probably wanted to reuse 3 of the 4 conditional code bits for, similar to RISC V, for having 32 general purpose registers, although they have only 31. Anyway, so just some introduction, exception model, security, all this fun stuff. Whether does it even start? So much to closing this. So what changed? Just as I summarized, application profiles, execution state, data types, yeah, so vector formats of Aarch. So vector types, not really what I wanted. As usual, also they have a bfloat 16 format similar to Intel. Remember, Intel also recently added this to their. Why is this not what I wanted? Overview, introduction. Probably have been done. This is why you want to open this overview. Was this here of not really. I would have started this document somewhere more with that, but with some general introduction, but whatever, I guess. Let's see, somewhere we need to reach the state of registers. Where would it start? Darn. In my opinion, this also makes better documents, like better and worse documents. You see how much I scroll over here, all the information I did not want. Exception state, where are the registers? Darn it. Okay, let's skip to the encoding. Let's see, what do we have here? Instruction set. So the only thing that stays the same is the A64 instructions still are 32-bit wide. Really not what I wanted. So as I said, they have more registers. Somehow they had a page with that I unfortunately closed. They had a page with this. So you have, instead of 16, you have 31, I think. 31 registers. And the instruction encoding is also entirely different. Oh, come on. In that, nah. You don't, as I said, you don't have the conditional bits. Oops, always one click too many. Probably that is. Anyway, you get the idea. So you still can address the like word registers, 32-bit word registers with W, and the extended registers, new extended 64-bit registers with X, and otherwise they are numbered, as you see, just that you don't have this conditional bits anymore. And as I speculated in the part 1, most likely they also have done this, I think, as I speculated in the part 1, it's certainly relatively difficult to implement a really high performance, out of order and potentially speculating pipeline for an extremely high performance, like think epic thread ripping AMD Ryzen, when all the instructions are conditionalized on previous instruction. Let's see, what else do we have here? Some other stuff here is the floating point stuff now is mandatory. Previously, you have seen in the part 1 they had previously version 1, 2, and 3 and so on a Neon, and in ARM64 this is mandatory, so there is no software floating point anymore. By the way, here I'm implementer. Here you also see, by the way, some implementers. Also, now we scroll over. Fun enough, Intel implementer. Fun fact: Intel also once upon a time had an ARM processor. So in the CPU, some special registers. You can read who is the implementer, like ARM Limited, Broadcom. You have a fine list here of Cavium, Digital Equipment, DEC, Infineon, Motorola, Freescale, Nvidia, Applied Micro, Circuit Corporation, Qualcomm. So yeah, and the architecture bits of what is implemented there. Similar to CPU ID on the x86 side. Let's see if we... The search, by the way, not the fastest in Firefox. Wish here would be the summary, but as usual, let's see, ARM v8, where do we have this general purpose register file? And yeah, also, of course, similar to the regular integer instructions, they also expanded the single instruction multiple data floating point register file to 32 or 31 registers, in previous times 16, so doubling that, and 128 bits, so similar to Intel AMD AVX. Of course, you have that here as well. And as I said, whatever version here is mandatory, whichever that was. Yeah, anyway, so given these differences, that they completely re-architectured the instruction set architecture, and encoding makes working with these versions rather more difficult than others, MIPS, Spark, x86, where this is more similar. And basically all the disassembly, all the assembler, all the compiler stuff is vastly different. And this probably explains, back in the day I was wondering that the latest iPhones from Apple do not support 32-bit. And this maybe explains why, back in the day, once upon a time I was wondering why, but given that this execution state and decoding is so vastly different, it certainly makes sense for an implementer like Apple to entirely remove and eradicate the 32-bit execution and decoding state, certainly freeing a good 100,000 of logic gates there. And I wonder when other vendors will follow. Also, yeah, on the Apple App Store side, of course, it is easier to say from one year to another we don't support 32-bit anymore. On x86 Linux 32-bit ARM Linux, it might be somewhat more difficult. However, we neither on Android nor on, well, on Android maybe a little bit, with apps there, Android allows native development kit, NDK, native applications, but yeah, just recompile, or if you're, depending on how much assembly you have in there, recompile this and re-upload this. But otherwise, given how vastly different and higher performance Aarch64, A64 is, that I wonder when the first non-Apple vendors start to remove the A32, Aarch32 state from their processors. Let's take one more look. Yeah, so as I said, 31. So the registers, not really sure what they've done with the 31st registers. 0 registers. So apparently 31 is 0. This is why they call the 31 general purpose registers, because all bits set is 0, register set are. That certainly makes sense and is what we have seen in other architectures. Also, usually R0 is 0, but on ARM, yeah, there you see the difference. On most RISC architectures, R0, the 0 register 0, except at the exception ARM64 register 31 is a 0 register. So yeah. So yeah, there we have this, and also X30 general purpose register is procedural calling register. So some, as per usual, there are some calling conventions, and of course you can general purpose freely use them, but for function calls and returns there are certain conventions, as we've seen in Spark and others, that you have argument and return and link registers for return addresses and so on, that you can use somewhat freely, but not, well, depending on what kind of use you make, may not always be able to clobber completely. So what else do we have here? That's basically it. The instruction encoding, we could take a look, but yeah, conditional flag, of course it still has conditional flags there in the processor state of negative, 0, carry and overflow, and IRQs and stuff, but and of course all those videos did not cover, of course you always have system registers, also your cache ID debug registers, all this processor specific stuff that would be too much to cover in this brief overview. What else do we have here to comment in the audience? A64 mode is much more RISC than A64, and says Avid. And well, yeah, I would certainly A32 is RISC, but as I said in part 1, and what I meant with this conditional, well, it's certainly RISC, but it's certainly simplified, especially with this conditional bits. Certainly it is not really necessary, and probably not the SVC, probably not the best bits used in the encoding space for this, for conditional bits. Certainly doubling the registers much more usable, and yeah, certainly makes sense. And so it's certainly somewhat cleaned up from this historic stuff. You would have thought ARM could have done this already in the 11 or so revisions before, but yeah, compatibility, although they have broke compatibility quite sometimes with floating point stuff, but yeah, certainly this is why A64 is much more preferable to A32, and I would certainly agree that it's much more cleaned up and certainly easier to decode for the processor. More registers are always nice to have, and yeah, that's probably it. They also had a really crazy store instruction. So A32, they had a really crazy, do we find this quickly? So that that something is RISC does not always mean that it's super simple. A32 had a really fancy multi-register load and store that they removed for ARM64. Where would this be? Yeah, like ordered regions of special load of whatever this instruction was, that allowed to load and store quite some region. What was this? Can we find this with ARM region load store? Anyway, you get the idea. This instruction is also not available in that form anymore. Do we have, as I said in the part 1, there is this scaling. Let's see, scaling. Do we find this quickly? Because there are some offset and scaling bits. That would be nice to document here. So load store. Do we have here load store register? Anyway, I studied computer science. Yes. Load store register. Where was this going? But most of the stuff I learned before university and after. It's not like they teach this on a recurring basis. Let's give this one more shot with ARM ISA. Overview. I think I once had a really nicer instruction set overview. I wanted to not the most helpful. Let's see this, or where would that be? I could actually, you know what, let's pause the stream for a second. I short look as if you want to ask some questions, and I will be back online, just not to archive you 1 minute of searching in the. So maybe this was the document I meant. Where would that be? Because this is a little bit nicer overview. How far are we? Nicer overview that we quickly scrolled over. Let's hope they didn't remove this. I think this was an operand 2. But this is also what I meant in my concept of what I want to do as a hobby, to write a small, stupid, most simple, just-in-time compiler. You see all the concepts are the same: arithmetic, logic, comparison, move, add, end, stuff, compare, move. This is what I would see, what kind of performance, or how easily we can target all architectures from ARM to x86. And with as least code and as, let's see what performance we get. Shift, I mean, yeah, it's by the way, yeah, if you are new to this document is actually not too bad to learn what shift here is, like logical and shift. So maybe that is actually this is supposed to be like this. Welcome everyone. So shift, it's yeah, generic stuff, not interested in this. ARM conditional instruction. I was actually load store instruction, specifying the address. Maybe that is that. Where would be, is it pre-index, post-index, then like update in yes, but this is funny. Accessing multiple memory locations, A64 provides load pair, LDP and store pair instructions data read or written to or from adjacent memory locations, so that you can load here multiple words at a time or double words. Where would be prefetch memory? I'm pretty sure you could scale this operand to. Where would this be? Scale 7-bit, what was that? Accessing, so LDP only base register with a scale 7-bit signed immediate value with an optional pre-post increment. Yeah, whatever, somewhere it was, but as per usual when you try to find it live on YouTube, you might know 64. Here's a general opcode family region here, as you see, and then this is the here's the destination register, operand register, and the second operand. It's of course, in my opinion, a little bit unsorted, but this is what I meant here. This operand 2, this was the shift I'm talking about, so I didn't fantasize that. So this is a shift applied to RM. So how the way this works, as you see here, this 12 bits of operand 2, and as they indicate here, so here's the second operand register and shift applied, so this is shifted. If you wanted to, similar to what it's used for, it's used to index into structures, into arrays, like word, double word arrays, or other data processing, whatever. And similar to x86, where we had the same base and scale system. And so if the 0, if the second operand is a register, and 1 here, if 1, the operand 2 is an immediate value, as you see, then you have here a 8-bit value plus a shift applied to the immediate value here. And yeah, this is how, as you see, how still the difference between RISC, reduced instruction set, also certainly RM is RISC in terms, initially people said A64 mode is much more RISC. Well, A32 was RISC, mostly first classification criteria of load instructions, like load, processing, store, in contrast to CISC, where you often can load and store within the instruction, but also this more not variable length, but more unified and fixed length instruction encoding. And you see, you can still cram in here some shifting and rotate and immediate stuff that you need for mapping higher level languages like C, C++, Rust, and so on to your processor. And we are probably mostly through. I hope you learned something, although the 64-bit version, as I was often trying to find stuff in the documents, as you see, I would probably structure the documents more like introduction stuff, and in my opinion, maybe not the super most easy to follow and find stuff instructions. We are mostly through. Of course, we could do this forever and take a look at Z80 and Motorola 68 and Super H and so on. Leave in the comments below what other instructions and architectures you want covered, if any. But we will also continue here on this channel not only making dedicated videos of this stuff like Xeon 5 and Revo and other BeagleBoard and Raspberry Pi here on this channel, but also writing a just-in-time compiler or compiler, because as I said, I'm somewhat curious. There is Lua JIT that does support some architectures, but I'm somewhat curious how tiny and yet readable you can get this and what kind of performance you can get out of this. I'm a little bit surprised that the computer science and open source community does not have this. Of course, there are some. There is from, maybe never heard about this, Perl 6 and Parrot. That is a Perl core development of what? Hello, not what I meant. Parrot virtual machine of also of Parrot Foundation. Raise your hand. I really wonder who is using Parrot. I have the feeling this Parrot in the works for 20 years or so. Yet does someone use it? Even leave in the comments below if you ever heard about this or using this. Of course, you can use LLVM as JIT, but LLVM is previous videos super large, and in latest days for GCC wanting to be competitive, you can even use GCC, libGCC for JIT, just-in-time compilation, but also huge, and certainly a lot of languages and emulators like PHP in the latest version, maybe PHP 8 or whatever is the latest version. Not the greatest PHP fan, but let's look this up. Also not loading because maybe not PHP, .NET, obviously not .org. I think PHP 8 maybe has a JIT so much too. How many decades does it take? JIT in PHP 8 maybe. And I'm a little bit surprised that we don't have a better infrastructure. As you see, there are quite some, also many emulators like N64, even Amiga. PS3 probably have dedicated JIT, just-in-time translation, and not to mention QEMU for TCG for Z. But yeah, maybe the people of Parrot tried, but maybe they tried to do everything in the kitchen sink and the end result, I don't know. I also tried to compile it recently, also the modern stuff of build systems, and can't even configure, make, install. But in any case, leave in the comments below what you think. I hope you learned something from all the stuff. One stuff certainly, one takeaway is that A64 is somewhat completely re-engineered for better implementation silicon, higher performance, and something not happening too often, has not even happened in AMD64, where they mostly took one new prefix of previously increment and decrement instruction and used it as a 64-bit rex prefix override, and the whole instruction set is for the most part still the same, except similar there in AMD64. 16 general purpose registers, but there you also see the difference, right? Also this A64, ARM64, all the RISC architectures usually have more like 32 general purpose registers, and even the x86 64, AMD64, still only 16, but then of course on x86 CISC you can load and store with all the instructions, so yeah. But certainly this also is what makes the x86 instruction implementation so complex for all the decoding to micro-ops and then some macro-op fusion, but also load and store in the instructions to achieve this performance. So yeah. Anyway, these are all the differences. I hope you learned something. Leave me in the comments below what if you have any questions or what else you want to see. I continue with my stuff here on the Sunday, and hope to see you soon for all the next videos and live streams to come.